For as long as humanity has existed, we have gazed into the night sky with a sense of awe and wonder, haunted by a question that transcends culture, religion, and era. Where did all this come from? The stars, the galaxies, the darkness between them, what is their origin? Myths and sacred texts offered poetic visions of creation, the breath of a divine being, a cosmic egg cracking open, a primordial ocean stirred by gods. But it was only in the 20th century that science began to construct a theory grounded not in belief, but in evidence. A theory bold enough to suggest that the universe, in all its vastness, had a beginning. That theory is the Big Bang. The term itself began as a joke, coined mockingly by astrophysicist Fred Hoyle, who resisted the idea of a universe that wasn't eternal. But the data refused to bend to tradition. Observations made in the 1920s revealed something astonishing. Galaxies weren't static, they were receding from us. The farther away they were, the faster they seemed to be moving. This phenomenon, later known as Hubble's law, suggested that the fabric of space itself was stretching, expanding like the surface of an inflating balloon. And if you rewound that expansion, as one might run a film in reverse, all matter would collapse back to a single point, an unimaginably dense and hot origin, a singularity. From this singularity, some 13.8 billion years ago, space and time as we know them began. The universe was born not with a whisper, but with a roar of creation. In that first second, physics operated under extreme conditions. Temperatures and densities were so high that familiar matter couldn't exist, only pure energy and a seething broth of fundamental particles. The Big Bang wasn't an explosion in space. It was the expansion of space itself. Everything, every galaxy, star, planet, and atom emerged from that moment of genesis. Yet the story doesn't end with that elegant conception. Because science is not a static collection of facts but a living, breathing process of inquiry, every theory must stand against challenge. The more powerful our tools become, the more we see. And now, with the launch of the James Webb Space Telescope, humanity has for the first time the means to peer deeper into the cosmos than ever before, to look not just far, but back in time. Webb's infrared eyes pierce the veil of dust and distance, capturing ancient photons that began their journey billions of years ago. What it has seen is both awe-inspiring and unsettling. Galaxies so massive, so well-formed, and appearing so early in cosmic history that they strain the limits of our most established theories. Are these anomalies cracks in the foundation of the Big Bang model, or signs that our understanding is on the brink of a revolutionary refinement? This is the frontier where astronomy meets philosophy, where questions about stars become questions about ourselves. And as we examine the evidence, one thing becomes clear. The universe is not just expanding. Our knowledge must expand with it. To understand why these recent discoveries pose such profound questions, we must revisit the roots of observational cosmology, the painstaking journey that led us from a static vision of the cosmos to a dynamic, evolving universe. In the early 20th century, most scientists still viewed the universe as eternal and unchanging. Even Albert Einstein, despite developing the general theory of relativity, which naturally allowed for an expanding or contracting cosmos, initially resisted the idea. Disturbed by the implications, he introduced a mathematical fudge factor, known as the cosmological constant, to force his equations into predicting a static universe. But nature had other plans. In the 1920s, astronomer Vesto Slipher began measuring the spectra of spiral nebulae, faint smudges of light that were, as it turned out, galaxies far beyond our own. He noticed that nearly all of them exhibited redshifts in their spectral lines, meaning they were moving away from Earth. Then, in 1929, Edwin Hubble provided the missing link. By measuring the distances to these galaxies using standard candles like Cepheid variables, he demonstrated a clear correlation between a galaxy's distance and its velocity. The farther away it was, the faster it receded. This became the cornerstone of what we now call the expanding universe. At the time, this notion was revolutionary. If everything was moving apart, then at some point in the past, it must have been much closer together, compressed, dense, and hot. The implications were staggering. The universe had a beginning, a moment when time and space themselves were born. The Big Bang theory emerged from this realization, providing a coherent narrative for the cosmos: expansion, cooling, formation of particles, atoms, stars, galaxies, and eventually planets and life. But science is not content with sweeping stories. It demands numbers, mechanisms, predictions. Over the decades, the Big Bang model became more refined. It successfully predicted the abundance of light elements, hydrogen, helium, and traces of lithium formed during the universe's first 3 minutes in a process known as primordial nucleosynthesis. It forecasted the existence of the cosmic microwave background radiation, the afterglow of the Big Bang, detected in 1965 by Penzias and Wilson as a faint radio signal coming uniformly from all directions. Later, satellite missions like COBE, WMAP, and Planck measured this background with increasing precision, confirming the model's predictions to astonishing degrees. Still, for all its triumphs, the Big Bang model has always left certain gaps unexplained, questions about the nature of dark matter, dark energy, and the precise mechanisms of inflation, a brief period of exponential expansion in the universe's infancy. The community has addressed these gaps with ever more complex theoretical scaffolding. And that scaffolding, until now, has held. But the observations coming from the James Webb Space Telescope are beginning to shake that structure. By capturing infrared light from the most distant, earliest galaxies, Webb offers a glimpse into the epoch less than 1 billion years after the Big Bang. And what it sees may not fully align with the expectations set by standard cosmological models. Some of these galaxies appear to be too large, too mature, and too chemically evolved for their cosmic age. If confirmed, this would suggest that the process of structure formation in the early universe was faster, more chaotic, or simply more mysterious than previously thought. In the world of science, such anomalies are not threats to be silenced, but opportunities to deepen our understanding. As history shows, every time we sharpen our vision, the universe rewards us with surprises. And right now, thanks to the James Webb Space Telescope, we are seeing further and questioning more deeply than ever before. When we talk about the early universe, we are not simply imagining a faraway place. We are looking back in time. Due to the finite speed of light, every distant object we observe reveals a past version of itself. A galaxy 1 billion light-years away shows us how it looked 1 billion years ago. The further we gaze, the younger the universe becomes. And with the James Webb Space Telescope, we are now peering into a cosmic epoch just a few 100 million years after the supposed moment of creation. The standard Big Bang model predicts a logical sequence. After the initial singularity, the universe expanded and cooled. Within the first few minutes, light nuclei formed, but it would take hundreds of thousands of years for electrons and protons to cool enough to combine into neutral atoms, allowing photons to travel freely, a moment known as recombination. This gave rise to the cosmic microwave background, the oldest light in the universe. Following this, a long period of darkness prevailed, where no stars yet existed, only vast clouds of hydrogen and helium drifting through an expanding, cooling void. Then, gravity began to take its role in earnest, slowly drawing matter together into dense regions where the first stars ignited, marking the beginning of what cosmologists call the cosmic dawn. Simple models suggested that galaxies would require hundreds of millions of years to assemble. Structures as massive and complex as the Milky Way were thought to be the result of gradual mergers and accretions spanning billions of years. Yet now, with Webb's unprecedented sensitivity, we are seeing luminous galaxies just 200 to 300 million years after the Big Bang, structures that seem to defy the time required to form them under standard scenarios. These early galaxies are not just faint smudges. Some display mature features, organized shapes, well-defined disks, and even evidence of chemical enrichment from multiple generations of stars. In other words, they look evolved. But how could so much structure, so many heavy elements, and such concentrated masses exist at a time when the universe was still in its infancy? One possible explanation is observational error. Perhaps what we are seeing is not what we think. Measuring the age and distance of galaxies relies on interpreting the redshift of their light, which can be skewed by dust, unknown physics, or instrumental limitations. Many of the most distant candidates discovered by Webb have yet to be confirmed spectroscopically. Photometric redshift estimates, based on color alone, can be misleading. But assuming the data holds, we face an exciting conundrum. Perhaps star formation was more efficient in the early universe than models predicted. Perhaps there were unknown mechanisms, like exotic cooling processes, massive inflows of gas, or the influence of dark matter, that accelerated galactic assembly. Or perhaps the scaffolding of the Big Bang model itself needs refinement, not rejection, but evolution. Science thrives on such moments. The telescope has opened a window not just to the edge of the visible universe, but to the edges of our understanding. It is revealing a cosmos that is not only stranger than we imagined, but perhaps stranger than we can imagine. And in doing so, it forces us to confront a fundamental truth of science. No theory is sacred. Only evidence is. To confront these cosmic puzzles, we must also understand the machinery of measurement, how astronomers extract knowledge from faint points of light scattered across the void. At the heart of modern cosmology lies a deceptively simple principle: the redshift. As light travels through the expanding universe, its wavelength stretches, shifting toward the red end of the spectrum. The further a galaxy is, the more stretched, more red its light becomes. By measuring this redshift, astronomers can estimate how far away a galaxy lies, and, by extension, how long its light has been traveling. But redshift alone does not tell the whole story. There are different types: cosmological redshift due to the expansion of space, Doppler redshift due to motion, and gravitational redshift due to massive objects warping space-time. Separating these signals requires precise data and careful interpretation. For truly distant objects, we must rely on infrared observations because the ultraviolet and visible light emitted by young stars in early galaxies has been stretched far beyond what our eyes, and even many telescopes, can see. That's where the James Webb Space Telescope shines. Its instruments are specifically designed to capture this ancient, stretched light. However, Webb's observations are not yet definitive. While its photometric capabilities are extraordinary, it still lacks the spectroscopic power of future telescopes designed to dissect the light from these early galaxies in fine detail. Without a clear spectrum, an unambiguous barcode of the elements and their velocities, we are left with estimates and probabilities. The suspicion arises: could some of these ancient-looking galaxies be imposters? Could they be dusty, lower redshift systems masquerading as primordial structures due to their unusual colors? This is why the next generation of telescopes is already under construction. The Extremely Large Telescope, ELT, currently being built in Chile with a staggering 40-meter primary mirror, promises to deliver the light-gathering power necessary to analyze these dim, distant galaxies in ways Webb cannot. With it, astronomers hope to obtain clean spectra of the earliest structures, confirming their age and composition beyond doubt. And yet, even with perfect data, interpretation remains complex. Consider the presence of heavy elements in young galaxies, elements like carbon, oxygen, and iron that should not exist in abundance if these systems had only just formed. Such elements are forged in the cores of stars and spread throughout the cosmos by supernovae, explosions that occur only after millions or even billions of years of stellar evolution. So how do we explain their presence so early? Some propose that the first stars, so-called population 3 stars, were vastly more massive than those we see today. Burning hot and fast, they would have lived short lives and seeded their surroundings with heavy elements almost immediately. Others suggest that massive black holes formed surprisingly early and triggered accelerated star formation by disturbing their galactic environments. Still others hint at exotic forms of matter, or even new physics at play. Each possibility is a thread waiting to be pulled. And as these threads unravel, we are reminded that cosmology is not a fixed tapestry, but a living weave, expanding, evolving, and full of mystery. The Big Bang Theory has withstood many tests, and it remains our most successful framework for understanding the universe. But even the strongest theories must bend when the sky itself begins to whisper new truths. The universe's earliest epochs remain shrouded in mystery, not just because of distance, but because of their extreme physical conditions. Conditions we cannot reproduce on Earth, and which only leave subtle fingerprints behind. One such fingerprint is the cosmic microwave background radiation, a pervasive field of microwaves that fills the cosmos. It is the afterglow of the Big Bang, the fossil light from when the universe became transparent, about 380,000 years after its birth. Before this time, the universe was a hot, dense plasma, opaque and chaotic. But as it cooled, electrons and protons combined to form neutral hydrogen, and light was finally free to move unimpeded. That ancient light still travels across the cosmos and reaches us today as a near-uniform glow at a temperature just above absolute zero. This cosmic microwave background, or CMB, was first detected by accident in 1965 by Arno Penzias and Robert Wilson, and its discovery provided one of the most compelling pieces of evidence for the Big Bang Theory. Later missions like COBE, WMAP, and Planck mapped the CMB in astonishing detail, revealing tiny fluctuations, regions of slightly different temperatures and densities. These fluctuations are crucial. They represent the seeds of all future structure. Without them, gravity would have had nothing to work with. The universe would have remained a uniform, expanding cloud of gas forever. But those tiny differences, just 1 part in 100,000, grew over billions of years into stars, galaxies, and clusters. This process, called gravitational instability, is a pillar of cosmological modeling. It explains why the universe today is so richly textured. And here lies one of the greatest achievements of the Big Bang framework, its ability to predict these structures from initial conditions we can observe in the CMB. It's not just a theory of the past, it's a map of cosmic evolution that connects the birth of light to the formation of worlds. Yet what Webb is revealing may demand a rethinking of how quickly that evolution occurred. If well-formed galaxies exist only a few 100 million years after the Big Bang, then the process of gravitational collapse must have happened faster than expected. Either the early universe was denser in ways we did not anticipate, or the physics of structure formation is incomplete. Some astronomers have proposed that massive black holes, appearing almost immediately after the Big Bang, could have served as gravitational anchors, pulling matter together into galaxies far earlier than predicted. This possibility introduces a provocative twist. For decades, We've believed that galaxies form first and black holes later as a byproduct of dense star clusters collapsing in their centers. But what if that order is reversed? What if supermassive black holes came first, remnants of strange conditions during the earliest moments of cosmic time? Could they be the scaffolding around which galaxies were built, rather than their central consequences? We don't yet know, but the idea is not without precedent. Throughout science, history has shown that our intuitive models are often inverted by new evidence. Planets were once thought to orbit Earth. Diseases were once blamed on imbalance, not infection. The universe may be telling us once again that our instincts are wrong, and that its story is richer, more complex, and more magnificent than we ever imagined. The suggestion that black holes may precede galaxies is not only bold, it reshapes the very narrative of cosmic genesis. Traditionally, supermassive black holes were believed to form gradually as stars died and their remnants collapsed under gravity. Over time, these remnants would merge and accrete matter, growing larger within the gravitational centers of galaxies. But Webb's observations hint at something more ancient, more abrupt. Black holes with masses equivalent to hundreds of millions, even billions, of suns appearing when the universe was only a few 100 million years old. From where could such enormous structures arise so quickly? If the early universe was a violent, unstable arena of extreme energies, could certain regions have resisted the general expansion? Could pockets of matter have collapsed inward before galaxies had time to form? One theory proposes that, in the very first moments of the Big Bang, fluctuations in density might have created primordial black holes directly, objects born not from dying stars, but from the chaos of the universe's own birth. These black holes would not be the end products of stellar life cycles, but the first enduring structures of the cosmos. If this is true, then our cosmological timeline must be redrawn. Instead of galaxies giving birth to black holes, it might be that black holes seeded galaxies, that these dense, invisible wells of gravity became cosmic architects, pulling in matter, igniting star formation, and shaping the universe's large-scale structure from the shadows. It's an inversion of cause and effect, and though speculative, it elegantly explains the presence of such massive, mature systems in an infant cosmos. But science demands more than elegance. It demands evidence. To test this hypothesis, astronomers must measure the masses, ages, and environments of these ancient black holes. They must observe the chemical fingerprints of their host galaxies, searching for signs of rapid star formation or violent interactions. They must simulate early universe conditions with increasing fidelity, pushing supercomputers to recreate what telescopes suggest. Already, theoretical models are racing to keep up with the data. Some posit that gas cooled more efficiently in the early universe, allowing matter to collapse faster. Others suggest that dark matter played a more aggressive role, forming dense halos that funneled ordinary matter into compact regions. And still others argue that what we see may be a consequence of cosmic variance, a statistical outlier in an otherwise predictable process. But perhaps the most exciting aspect of this debate is what it reveals about the nature of science itself. Every time our instruments become more sensitive, every time we open a new observational window, we are confronted with anomalies. These are not failures of theory, but invitations, challenges that force us to refine our understanding, to abandon cherished assumptions, and to embrace the unknown. The James Webb Space Telescope is not just a machine for looking at stars. It is a time machine, a truth machine, and a mirror held up to the limits of human knowledge. As it peers into the darkness, it reminds us that discovery always begins with a contradiction, a flicker of doubt that pierces the certainties we once held sacred. And in that flicker, the future of cosmology is born. As we push deeper into the cosmic past, another question emerges, one that strikes at the heart of both theory and observation. How much of the universe are we truly seeing? The term observable universe is often misunderstood. It does not refer to all that exists, but merely to the portion from which light has had time to reach us since the beginning of cosmic time, about 13.8 billion years. Due to the ongoing expansion of space, this horizon currently stretches to a diameter of roughly 93 billion light-years. But beyond that limit, the universe continues, perhaps infinitely, and perhaps in ways that defy our comprehension. This leads us to a sobering realization. All our measurements, all our data, all our cosmic maps are based on an incomplete picture. We study galaxies, radiation, and structure within a bubble defined by light and time, unaware of what lies just beyond its reach. The James Webb Space Telescope, though a marvel of modern engineering, operates within this boundary. It extends our reach closer to the edge, but not beyond it. And so, our theories remain grounded in the visible, a fraction of what may be. Critics of the Big Bang theory often exploit this limitation. They argue that if we cannot observe the entirety of the universe, how can we claim to understand its origin? Some take this further, accusing mainstream science of arrogance, or worse, collusion. They paint researchers as gatekeepers of an official narrative, unwilling to entertain alternatives. But this caricature ignores the reality of scientific culture. In truth, science thrives on challenge. Peer review, replication, and open discourse form its foundation. Every theory, including the Big Bang, must continuously withstand attack, adaptation, and evolution. Indeed, even within the halls of academia, dissent exists. Researchers propose alternative models, cyclic universes, bouncing cosmologies, modified gravity. Some of these ideas are mathematically elegant, others fantastical. But all are welcome, provided they do what every scientific theory must: make testable predictions and align with observation. The issue is not whether alternative voices are allowed, but whether their models can survive scrutiny. One vocal critic of the Big Bang, Eric Lerner, gained notoriety for his claim that the theory is fundamentally flawed and that observational data has been misinterpreted or ignored. Lerner argues that the universe has no beginning, and that what we interpret as redshift is not due to expansion, but some yet unknown mechanism. His critiques, however, often rely on outdated data or misrepresentations of modern cosmology. More crucially, they fail to offer a predictive framework that can compete with the explanatory power of the Big Bang model, a model that has accurately forecasted everything from the temperature of the cosmic microwave background to the abundance of light elements. Still, critics like Lerner serve a purpose. They force the scientific community to sharpen its arguments, revisit its assumptions, and remain vigilant against complacency. In this way, even flawed opposition contributes to the robustness of the system. Science is not threatened by challenge. It is animated by it. The real danger lies not in disagreement, but in dogma, the refusal to consider new evidence or to revise long-held beliefs in the face of change. And so, as Webb continues to return its golden-eyed gaze to the early universe, cosmologists find themselves at the threshold of a new era, not one of crisis, but of refinement. The Big Bang theory still stands, not as an unshakable monument, but as a living theory, one that must grow and flex as the cosmos reveals more of its secrets. One of the most profound strengths of the Big Bang theory lies in its predictive power. It does not merely explain what we see, it tells us what we should expect to find. Decades before we had the tools to test it, the theory foretold phenomena that would later be discovered with stunning accuracy. The cosmic microwave background was predicted long before its accidental detection in 1965. The exact ratios of hydrogen and helium observed throughout the cosmos match the model's calculations for nucleosynthesis in the first 3 minutes of existence. Even the distribution of large-scale cosmic structures, filaments of galaxies stretching across space like a cosmic web, has been simulated and verified by observations. This ability to predict, verify, and refine is what gives the theory its scientific legitimacy. But what happens when new observations seem to defy the model's timeline? This is precisely the challenge presented by the James Webb Space Telescope. Some of the galaxies it has imaged appear to be forming stars and accumulating mass at speeds far beyond what the standard model allows. These are not faint, chaotic smudges. They are massive, structured, and in some cases, chemically enriched, attributes that suggest a level of maturity impossible to achieve within just a few 100 million years of cosmic time, unless we are missing something crucial. One possible explanation is that the early universe was denser than we previously believed. If matter was more tightly packed in the beginning, gravitational collapse could have happened faster, compressing gas into stars and galaxies at a pace much quicker than current models predict. This scenario would not invalidate the Big Bang, but it would require adjustments to parameters, tweaks to the initial conditions, or refinements in our understanding of dark matter's role in the process. Another possibility is that star formation in the early universe followed a different set of rules. Modern star formation is influenced by a variety of factors: gas temperature, magnetic fields, turbulence, feedback from supernovae. But the first stars, so-called population 3 stars, formed in a different environment. They may have been more massive, more efficient, and shorter-lived, leading to a rapid cycle of birth, death, and element dispersal that accelerated the evolution of their host galaxies. There's also the role of mergers and interactions. In the modern universe, galaxy collisions are relatively rare and slow. But in the early cosmos, with everything closer together and moving faster, such interactions would have been more frequent and more violent. Galaxies could have grown not gradually, but through a chaotic process of repeated collisions, an early period of cosmic cannibalism that forged complex structures faster than we imagined. And yet for all these adjustments and hypotheses, the fundamental question remains: are these early massive galaxies genuine outliers, or are they common and thus symptomatic of a deeper gap in our theory? The answer requires better data, more precise redshifts, full spectra, chemical composition profiles. Some of this information is already trickling in, but full confirmation may await the next generation of instruments, ground-based giants like the ELT, and space missions yet to launch. What we do know is this: these new observations, far from dismantling the Big Bang, are setting the stage for its evolution. They are pushing theorists to ask better questions, to refine the model's assumptions, and to dig deeper into the hidden rules of cosmic structure. This is how science moves forward, not by rejecting old frameworks out of hand, but by challenging them to account for the new, the unexpected, and the extraordinary. As the implications of these early galaxies sink in, we are forced to consider yet another layer of cosmic mystery: time itself. When we say that a galaxy formed 300 million years after the Big Bang, we're not just marking a date. We're referencing an era when the entire fabric of the universe was radically different. Time, as we experience it, is bound to the flow of space and matter. In those first cosmic moments, the density, temperature, and even the rate of time's progression may not align with our intuitive understanding. This adds subtle complexity to the challenge of modeling such epochs. Cosmological time is measured not by calendars, but by transitions, by what was possible when. The birth of light, the cooling of plasma, the formation of atoms, the ignition of stars, each of these events is a milepost along the arrow of time. But if we are now observing galaxies and black holes forming earlier than any model predicts, perhaps we must reconsider how we understand that arrow. Perhaps the early universe was governed by processes so unfamiliar that our current models cannot fully account for them. The early universe, after all, was not simply smaller, it was more compact in every sense. Matter, radiation, and even quantum fields interacted in close quarters under extreme energies. Under these conditions, new physics may emerge, physics that breaks down at lower energies and densities, and thus remains hidden from modern particle accelerators. Some physicists speculate that exotic states of matter, or phase transitions in the quantum vacuum, could have altered the way gravity or radiation behaved in that primordial epoch, enhancing structure formation or triggering black hole birth far more rapidly than we currently assume. There is also the speculative yet compelling idea of inflation, an incredibly rapid expansion of space during the first tiny fraction of a second. This inflationary epoch smoothed out the universe and seeded the tiny fluctuations in density that would later become galaxies. But inflation itself is still not fully understood. What caused it? What ended it? Could remnants of this process have created pockets of extreme density, perhaps even the precursors of the early black holes and massive galaxies Webb now sees? Some go even further, suggesting that we may live in a multiverse, a vast ensemble of bubble universes, each with its own physical constants, born from a chaotic inflationary landscape. In this view, our universe is just one realization of many, and the particular way our cosmos formed might not be typical at all. This idea, while difficult to test, offers a framework in which seemingly improbable observations, like mature galaxies appearing too early, might not be improbable at all, just one roll of a cosmic dice in a much larger game. Still, such concepts remain on the theoretical frontier. They are beautiful, bold, and, as of now, speculative. What grounds our understanding remains the data, and that data is growing every day. The James Webb Space Telescope is still early in its mission, and already it has rewritten the script for cosmic origins. In the coming years, it will peer even deeper, capture fainter light, and provide clearer windows into the past. Each new discovery will refine our understanding of how space, time, matter, and energy dance together to shape the universe we inhabit. And as we gaze further into that ancient light, we are reminded of a humbling truth. The more we learn about the cosmos, the more we learn how little we truly know. The interplay between observation and theory sits at the heart of cosmology. For decades, the field has flourished in a delicate balance. Astronomers uncover new patterns, and physicists craft explanations rooted in mathematical rigor. But when the observations begin to outpace the theories, a tension arises. It is not a failure, it is a spark. And right now, that spark is burning brightly. Among the most pressing puzzles sparked by Webb's data is the apparent contradiction in the timing of galaxy formation. According to standard cosmology, the timeline from the Big Bang to the emergence of the first large galaxies involves a long gestation. Dark matter clumps attract hydrogen gas. The gas cools and condenses. Stars form. Then galaxies gradually assemble through mergers and accretion. This process, governed by well-understood laws of gravity and thermodynamics, should take hundreds of millions of years to yield complex systems. But now, astronomers are seeing galaxies at just 200 million years after the Big Bang that seem as massive and organized as galaxies that should have taken 1 billion years to form. These are not anomalies. More of them keep appearing. Their light, stretched by cosmic expansion, bears the fingerprint of age and distance. Their spectra, although sometimes preliminary, suggest mature stellar populations. The natural question follows: did these galaxies form faster, or did our model timelines stretch too long? To reconcile this, cosmologists are revisiting everything from initial density fluctuations to the behavior of dark matter. Some suggest that the early universe's matter distribution may not have been as smooth as the cosmic microwave background implies. Others explore the properties of dark matter itself. Perhaps it interacts more strongly, clumps more efficiently, or played a catalytic role in the rapid coalescence of structure. Then there's the more radical possibility that our understanding of gravity, so solid within galaxies and solar systems, may not scale cleanly to the vast canvas of the universe. Modified gravity theories such as MOND, modified Newtonian dynamics, or emergent gravity frameworks attempt to explain cosmic structure without invoking dark matter. Though still fringe, these models are gaining renewed attention as standard cosmology faces tension with observations. At the same time, observational techniques are also under scrutiny. Determining the redshift of extremely distant galaxies is notoriously difficult. Without high-resolution spectra, photometric estimates can be misleading, mimicking ancient light through dust reddening or peculiar star populations. Webb's instruments are powerful, but even they have limits. Many of the claimed ultra-distant galaxies await confirmation through spectroscopic methods that can definitively anchor them in time and space. Meanwhile, ground-based observatories equipped with adaptive optics are stepping in to complement Webb's reach. The next decade will see a convergence of instruments: Webb, the ELT, the 30-meter telescope, TMT, and the Vera Rubin Observatory, all working together to map the early universe in unprecedented detail. These observatories will not only confirm redshifts, but reveal internal dynamics, star formation rates, and chemical compositions of the earliest galaxies. This synergy between observation and theory is where real breakthroughs happen. Just as Galileo's telescope shattered medieval cosmology, so too might Webb and its successors force a new paradigm. Not because the Big Bang is wrong, it still explains the broad strokes of cosmic evolution with elegance, but because it may be incomplete. Like Newtonian physics before relativity or classical mechanics before quantum theory, our current model may soon give way to something deeper, something that unifies what we see with what we expect. And so, as scientists push the boundaries of knowledge, the universe responds, not with answers, but with questions deeper and more profound than before. The cosmos is speaking in the language of light. It is up to us to learn how to listen. As we peer deeper into the ancient universe, the very idea of what counts as normal is being rewritten. Take, for instance, the discovery of heavy elements, carbon, oxygen, nitrogen, even iron, within galaxies that supposedly formed just a few 100 million years after the Big Bang. This is not a minor detail. According to the standard narrative, the earliest stars, known as population Threeg stars, were forged from pristine hydrogen and helium, the only elements created during the primordial nucleosynthesis that followed the Big Bang. These stars were thought to be massive, hot, and short-lived, blazing through their nuclear fuel in mere millions of years before ending their lives in cataclysmic supernovae. Only then, through such stellar deaths, could heavier elements begin to seed the universe. So, how do we explain galaxies rich in metals, astronomical parlance for all elements heavier than helium appearing so soon? Their presence implies not just the birth and death of one generation of stars, but possibly two or more. It suggests a level of cosmic recycling, of enrichment, that seems far too rapid for the brief time that had elapsed since the universe's origin. Is our picture of stellar evolution in the early universe incomplete? Or are the timelines shorter than we believed? This puzzle grows more intriguing when paired with evidence of black holes at the centers of these early galaxies. Some of them appear to host quasars, intensely bright beacons powered by matter spiraling into supermassive black holes. These phenomena require not only the existence of enormous black holes, but also a ready supply of gas and dust to fuel them. And again, they seem to appear earlier than any model currently predicts. Astronomers are thus faced with a cascade of cosmic contradictions. Early galaxies are too bright. Their stars are too old. Their black holes are too massive. Their environments are too complex. And yet, the data are increasingly consistent. What once might have been dismissed as observational error or statistical fluke is now taking on the weight of evidence. Several potential solutions are on the table. One is that star formation in the early universe was more efficient than we thought. Without the hindrance of metals to cool gas clouds slowly, primordial hydrogen and helium may have collapsed more rapidly, igniting starbursts on massive scales. Another possibility is that these galaxies formed in regions of the universe where matter was particularly dense, cosmic hotspots where gravity took hold earlier and more forcefully than average. A third hypothesis suggests that black holes formed not from stellar collapse, but directly from collapsing gas clouds in the early universe, a process called direct collapse. If true, it could explain how black holes with masses of millions or billions of suns came into being so quickly. It would also invert our traditional timeline, positioning black holes not as the byproducts of galactic evolution, but as catalysts for it. Gravity wells around which galaxies themselves coalesced. These ideas are not mutually exclusive. In fact, the truth may lie in a complex interplay of all three. And while these hypotheses remain under investigation, what they share is a recognition that our current models are being stretched, perhaps not to breaking, but certainly to the brink of revision. The James Webb Space Telescope is not merely delivering beautiful images of distant galaxies. It is excavating the deep past. And with each ancient photon it captures, it offers not certainty, but confrontation. We are no longer just affirming theories. We are being asked to rewrite them, not because the Big Bang is wrong, but because the universe is more agile, more efficient, and more surprising than we ever dared imagine. The evolving portrait of the early universe challenges not just our cosmological assumptions, but the very way we approach scientific truth. There is a subtle but vital distinction between what we know and what we assume. The Big Bang theory has, for decades, offered an elegant scaffolding for our understanding of the cosmos. It ties together redshift, cosmic background radiation, light element abundances, and the large-scale structure of galaxies in a single cohesive model. And yet it has always included blind spots, regions of uncertainty we've filled with placeholder concepts like dark matter, dark energy, and inflation. These aren't empty guesses. They are deeply mathematical, rooted in observation, but they are also markers of the unknown. Now, with the flood of data from James Webb and its successors, we are approaching these unknowns with greater clarity and greater humility. Dark energy, for instance, is still an enigma. First inferred from supernova observations in the late 1990s, it appears to be accelerating the universe's expansion. Yet we do not know its nature. Is it a property of space itself, a new field, or a misinterpretation of gravity? And if this mysterious force has shaped the cosmos over billions of years, could it also have influenced the early structure formation we now observe? Could its strength or behavior have varied in ways we never considered? Even more fundamental is the challenge of interpreting what we see. Light, after all, is not a perfect messenger. It can be bent by gravity, absorbed by dust, distorted by movement, and misread by instruments. Astronomers must disentangle each signal with care, aware that a single miscalculation in redshift or brightness can shift a galaxy's age by hundreds of millions of years. It is a task that requires not only cutting-edge technology, but immense patience. This is where the culture of science becomes critical. Contrary to popular belief, scientists do not operate in a vacuum of certainty. They debate, they doubt, they critique each other's work with the fervor of artists or philosophers. At conferences and in journals, Theories are dissected, models are stress-tested, and assumptions are laid bare. The goal is not to confirm one's own bias, but to survive the scrutiny of others. This spirit is what keeps cosmology dynamic. New theories emerge constantly, some conservative, others radical. There are those who propose that the universe has no beginning, that it cycles through phases of expansion and contraction. Others suggest the existence of mirror universes, where time runs backward or physical laws behave differently. These ideas are not universally accepted, but they are not dismissed out of hand either. They are part of a rigorous ecosystem of thought, where even the most audacious hypothesis must bow to the judgment of data. And so, when critics claim that science is dogmatic, that it clings blindly to the Big Bang and excludes dissent, they misunderstand its nature. Theories endure not because they are fashionable, but because they work. The Big Bang persists because, so far, it explains more than any alternative. But that could change. Indeed, change is inevitable. Every new discovery forces refinement. Every contradiction invites creativity. The universe is not static, and neither is our understanding of it. The James Webb Space Telescope, by peering further and deeper than any of its predecessors, is not just offering answers. It is widening the scope of our questions. It is redefining what we mean by early, massive, and even possible. And in doing so, it is reminding us that the search for truth is not a straight path, but a spiral, ever revisiting old ground with new eyes. As our understanding expands, the distinction between mystery and myth becomes increasingly important. For millennia, humans have looked up at the night sky and created stories, tales of gods, heroes, and dragons to explain the stars. Today, our narratives are shaped not by legend, but by data, mathematics, and physical laws. And yet, in this transformation, the sense of wonder has not diminished. If anything, it has deepened. Because now, instead of attributing the birth of galaxies to divine breath, we can trace them to thermonuclear processes, quantum fluctuations, and gravitational collapse, mechanisms as awe-inspiring as any creation myth. But this modern cosmology is fragile. It is not built on faith, but on evidence. Every equation must be tested. Every claim must be supported by what the universe reveals through its light. That light has carried secrets for billions of years, and now, with instruments like the James Webb Space Telescope, we are finally able to read them with greater precision. Among the most tantalizing secrets are those concerning the formation of structure in the early universe. As Webb pushes our gaze closer to the Big Bang, it captures galaxies with unexpected mass, shape, and chemical complexity. Some of them appear to be forming stars at rates that rival the most active galaxies today. They are compact, bright, and sometimes surrounded by halos of dust, hallmarks of mature systems, not newborns. These features should not exist so soon, and yet there they are. If the observations hold, and the community is proceeding with both excitement and caution, then we may be witnessing an entirely different mode of cosmic evolution. One where galaxies don't slowly assemble like architectural blueprints, but erupt into being through chaotic bursts of energy, fueled by dense matter reservoirs and perhaps even primordial black holes. This is not what our textbooks have taught, but that is the beauty of science. Textbooks are not final chapters. They are drafts. One emerging line of thought suggests that our current cosmological simulations may underestimate the power of gravity under extreme early universe conditions. The clustering of dark matter, the cooling of gas, and the formation of stars may have operated under slightly different rules when densities were higher and timescales shorter. A small change in initial conditions, say a slightly larger fluctuation in the early quantum field, could lead to vastly accelerated structure formation. Such a model would not overthrow the Big Bang, but it would significantly alter the tempo of cosmic evolution. Another compelling idea involves the feedback loops of black holes. Traditionally, black holes were viewed as endpoints, celestial sinkholes where matter vanished. But today, we understand them as engines of creation as well as destruction. As matter falls into a black hole, it heats up, radiates energy, and can even trigger shock waves that compress surrounding gas, igniting new star formation. In the early universe, such feedback might have amplified the growth of galaxies rather than stifled it, creating a cosmic chain reaction of explosive development. And all of this leads us to a deeper philosophical point. The universe does not care about our expectations. Nature is not obligated to follow our timelines, our assumptions, or our sense of plausibility. It simply is. The job of science is not to impose order upon the cosmos, but to uncover the order that already exists, no matter how strange, how unlikely, or how counterintuitive it may seem. We are now in a moment of profound transition. The observations coming in are not just refining our models, they are challenging our intuitions. The old boundaries between known and unknown are shifting. And as we step further into this new territory, we are reminded that the most powerful tool we possess is not any telescope or algorithm, but a willingness to be surprised. Surprise, in science, is not a sign of failure. It is a sign of vitality. When nature defies our predictions, it means we are truly probing the unknown. And nowhere is this more evident than in our ongoing exploration of the universe's earliest structures. The James Webb Space Telescope, with its unparalleled sensitivity to infrared light, has pulled back the veil on a time when the cosmos was less than 1 billion years old. But what it reveals is not a slow, tentative emergence of form. It is a riot of creation, dense clusters, blazing stars, massive black holes, all forming faster, brighter, and more chaotically than anyone expected. To reconcile these discoveries, astronomers are beginning to revisit the foundational assumptions baked into cosmological simulations. For years, computer models have served as our virtual laboratories. Digital universes seeded with known physics evolved over time to reproduce the structures we see today. But these models are only as accurate as the assumptions they contain. Many were calibrated using data from the Hubble Space Telescope and earlier instruments, which could not see as deeply into the early universe as Webb now can. As a result, some simulations may have underestimated the speed and scale of early galaxy formation simply because we lacked the data to suggest otherwise. Webb is now filling in that missing data, and what it's showing is compelling evidence that star formation in the early universe may have occurred in massive short-lived bursts. These early galaxies might have experienced violent episodes of starbirth, where tens of thousands of stars ignited within a few million years, a process far more efficient than previously modeled. Such rapid activity could explain their brightness and apparent maturity, even at high redshifts. This kind of behavior might also leave distinct chemical fingerprints. Supernovae from the first generations of massive stars would have seeded the surrounding gas with heavy elements, producing specific ratios of oxygen, carbon, and iron that future telescopes can measure. If Webb and its successors confirm these chemical signatures, it would lend powerful support to the idea of hyper-efficient early starbursts. But there is also a more profound implication. These observations suggest that cosmic evolution may not be smooth and gradual as once believed. Instead, it may be punctuated by bursts of rapid transformation driven by local conditions, density spikes, cooling thresholds, black hole activity that allow galaxies to leap forward in development. This shift in understanding mirrors changes in other scientific fields, like biology, where theories of gradual evolution have been supplemented by ideas of punctuated equilibrium, long periods of stability interrupted by sudden leaps of change. Could the cosmos itself evolve in fits and starts, with certain regions racing ahead of others? Could our own galaxy be the product of such a cosmic acceleration? These are no longer idle questions. They are the frontiers of research, and they may hold the key to understanding not only where we came from, but how common or rare our cosmic story might be. This brings us to an even larger question. If early galaxies formed so quickly, what does that say about the initial conditions of the universe? Were they fine-tuned? Were they typical? Or are we seeing only a small, atypical corner of a much larger, more varied cosmic landscape? Science cannot yet answer these questions, but it can ask them with growing clarity. And in doing so, it sharpens the edge of discovery, not just about galaxies and stars, but about time, structure, and the deep architecture of reality itself. The architecture of reality. That phrase captures the heart of cosmology. We are not just charting where galaxies are or when they formed. We are investigating the rules that govern the unfolding of the universe itself. These rules are encoded in the laws of physics, the constants of nature, and the shape of space-time. They determine how matter behaves, how gravity sculpts structure, and how light carries the message of creation across billions of years. And yet, the deeper we probe, the more these rules seem less like fixed commandments and more like emergent patterns, subtle, layered, and perhaps even variable in the universe's earliest moments. One area where this ambiguity is most pronounced is the mysterious realm of dark matter and dark energy. Together, they compose about 95% of the total mass energy content of the universe. We cannot see them directly. They do not emit or absorb light. Yet their influence is unmistakable. Dark matter provides the gravitational glue that holds galaxies and clusters together. Without it, galaxies would fly apart. Dark energy, meanwhile, appears to drive the accelerated expansion of the cosmos, a force so pervasive that it shapes the ultimate fate of everything we see. But what are they? No one knows for certain. We infer their presence from their gravitational effects, not from direct detection. Dark matter could be a new kind of particle, or it might signal a flaw in our understanding of gravity itself. Dark energy might be a property of space-time, or it could be the footprint of an unseen field or extra dimension. These ideas are not mere speculation. They are at the frontier of theoretical physics, and they matter deeply because any attempt to understand galaxy formation, especially in the early universe, must take them into account. It is possible that the rapid appearance of galaxies seen by Webb is not a contradiction to current models, but a revelation about how dark matter behaved under extreme conditions. Maybe it clustered more efficiently or interacted differently with ordinary matter in the high-energy environment of the early cosmos. Perhaps it even played a catalytic role, igniting the rapid starbursts and black hole growth that now defy expectations. Or perhaps dark energy itself, typically assumed to be uniform and constant, varied subtly over time, affecting the rate of expansion in ways not yet incorporated into our equations. These possibilities, while unconfirmed, highlight an essential truth. We are operating at the edge of what is known. The standard model of cosmology, often called LCDM, lambda cold dark matter, is remarkably successful. It describes the evolution of the universe from a fraction of a second after the Big Bang to the present day with impressive precision. But it is also incomplete. It includes elements, dark matter, dark energy, inflation, that are necessary to fit the data but remain mysterious in their nature. They are placeholders for deeper truths yet to be uncovered. And this is where the power of instruments like the James Webb Space Telescope becomes most apparent. By pushing observations to earlier and earlier epochs, Webb does not just test the known, it exposes the unknown. It places pressure on our models, forcing refinement, sometimes even revolution. And in doing so, it fulfills the highest purpose of science, to replace ignorance not with certainty, but with better questions. Because the pursuit of knowledge is not about arriving at a final answer. It is about refining our understanding again and again as the universe reveals itself one photon at a time. As the questions grow more sophisticated, the tools we need to answer them must evolve in parallel. The James Webb Space Telescope is not the endpoint of our observational journey. It is the beginning of a new era in astronomy. Already, the scientific community is preparing for the next wave of observational giants, telescopes on Earth and in space that will surpass even Webb in certain capacities. Together, they will form a coordinated fleet of eyes on the sky, each optimized to answer a different piece of the cosmic puzzle. On Earth, the extremely large telescope, ELT, in Chile, with its massive 39-meter primary mirror, will provide unprecedented angular resolution and light-gathering power. The 30-meter telescope, TMT, in Hawaii, and the Giant Magellan Telescope, GMT, in the Southern Hemisphere, will join it in transforming our ability to conduct deep spectroscopy. These instruments will resolve the faintest details in distant galaxies, dissecting their chemical compositions, measuring their motion, and verifying their ages with greater certainty than ever before. Spectroscopy, examining the specific wavelengths of light emitted or absorbed by matter, is the key to verifying redshifts, identifying elements, and determining star formation histories. In space, upcoming missions like the Nancy Grace Roman Space Telescope and ESA's Euclid will complement Webb by conducting wide-field surveys of galaxies across cosmic time. They will not look as far as Webb does, but they will look broadly, mapping the structure of the universe at large scales and providing the statistical context for Webb's deep, narrow views. Together, these instruments will allow us to understand not just individual ancient galaxies, but the entire population of early structures, how common they are, how they cluster, and how they evolve. But data alone is not enough. It must be interpreted within a theoretical framework. That is where computational astrophysics comes in. Advances in supercomputing are allowing researchers to simulate entire universes from first principles, modeling billions of galaxies under a wide range of initial conditions. These simulations incorporate not just gravity, but hydrodynamics, magnetic fields, radiative transfer, and feedback from supernovae and black holes. They are digital laboratories where we can test our hypotheses against what the telescopes see. Crucially, when Webb detects a galaxy that seems to defy expectations, too bright, too massive, too early, these simulations can be adjusted to see if such an outcome is plausible. If so, we refine our understanding of the variables involved. If not, we begin to suspect that something fundamental may be missing from our models. Perhaps a new process is at play. Perhaps the laws of physics behave differently under conditions we have not yet imagined. This iterative dance between observation and simulation, between theory and data, is how science advances. Each new discovery is like a stone thrown into a pond, sending ripples through the equations and assumptions that define our view of the cosmos. Sometimes the ripples fade. Sometimes they crash against the shore and reshape the landscape entirely. And this, in the end, is why the challenge presented by early galaxy formation is so exciting. It is not merely a technical puzzle. It is a chance to deepen our understanding of the universe's earliest moments, to glimpse perhaps not just how the cosmos began, but why it unfolds the way it does. Whether the answer lies in refined dark matter behavior, alternative inflation models, or entirely new physics, one thing is certain. The tools we are building today will unlock a far richer map of the universe tomorrow. With each new tool and each new observation, we come closer to an uncomfortable yet exhilarating realization. Our current understanding of the cosmos may only scratch the surface of a much deeper, more layered reality. For centuries, science has advanced through a process of accumulation, adding new knowledge to the old, refining, revising, but rarely overturning everything at once. Yet there have been moments, paradigm shifts, when the foundations cracked open and something entirely new emerged. The Copernican revolution, Newtonian mechanics, Einstein's relativity, quantum theory. Might we be on the brink of another such transformation? The discoveries being made by Webb and its fellow observatories do not yet demand a revolution, but they are pressing hard against the boundaries of our models. They are highlighting inconsistencies, revealing blind spots, and raising questions that our current framework struggles to answer without ad hoc adjustments. It is a familiar pattern. Observations grow too complex for the old model to handle cleanly, and a new, more comprehensive theory emerges, one that subsumes the old within a broader structure. Already, theorists are considering bold possibilities. Perhaps gravity itself behaves differently at high energies or small scales, suggesting modifications to general relativity. Maybe time and space, which we treat as continuous fabrics, are actually discrete at the Planck scale, emerging from deeper quantum informational processes. Or perhaps the early universe is just one pocket of a much larger multiversal ensemble, where different regions experience different physical laws entirely. These ideas are not science fiction. They are being explored in serious journals, at high-level conferences, and in the minds of the brightest physicists and cosmologists on the planet. Yet none of them has yet presented a complete, testable alternative to the Big Bang that can explain the full range of evidence as effectively. And so, the Big Bang theory persists, not as dogma, but as the best working model we have. It describes the cooling of the universe, the emergence of light, the abundance of elements, and the structure of space across billions of years. But it is also a framework that is beginning to stretch. Under the weight of Webb's data and the mystery of early galaxies, it may soon demand something more. And this is the moment when philosophy meets physics. When we are forced to confront not just how the universe behaves, but why we believe what we believe, why we trust certain equations, and why we organize reality in the way we do. The edges of cosmology are not merely technical, they are existential. They ask what it means to live in a universe that is vast, ancient, and perhaps unknowable in its entirety. But this is also the moment of greatest promise, because to stand at the edge of knowledge is to glimpse the next frontier, the next discovery, the next truth. The scientists guiding Webb, poring over spectra and images in quiet observatories and bustling research centers, are not just decoding data, they are sketching the outlines of a new cosmic narrative. A narrative in which galaxies form faster, stars shine sooner, and gravity itself may play tricks we never expected. A universe where the questions outnumber the answers, but where the pursuit itself is the answer. Because to seek is to grow, to question is to evolve, and to listen carefully and humbly to the light that has traveled for billions of years to reach us is to engage in one of the noblest acts of science and of humanity. As we lean into this new era of cosmic discovery, it becomes increasingly clear that the role of doubt is not a flaw in science, but its core engine. Doubt, in the scientific sense, is not skepticism for its own sake. It is a disciplined curiosity. It is the willingness to hold even the most cherished theories accountable to the evidence. And today, the evidence is whispering that the early universe may not have followed the script as closely as we once believed. The galaxies captured by the James Webb Space Telescope are rewriting what we thought was possible. Massive, structured, and chemically enriched, they seem to have formed not slowly and cautiously, but with explosive speed. Their black holes are already giants. Their stars are already recycled. Their light carries the fingerprints of maturity in an era that should have barely known fire. These are not trivial details. They are cracks in the facade of our best model. And while the foundation still holds, the strain is palpable. Yet this is not a crisis. It is an invitation. In every major scientific advance, there has been a moment when the data began to diverge from the theory, when small inconsistencies refused to vanish and instead multiplied. At first, they were considered anomalies. Then, as they piled up, they became catalysts. The failure to fit the model became the signal that a better one was needed. It happened with the orbits of planets, with the speed of light, with the atom, with the genetic code. And now, perhaps, it is happening with the origin and evolution of galaxies. To those outside the scientific world, this process can seem chaotic or even suspicious. Theories change, models shift, certainties dissolve. But this is precisely what makes science resilient. It is not a cathedral built once and protected forever. It is a ship, constantly rebuilt as it sails, each new plank laid with care, each old beam tested against the storm. And at the helm are people, flawed, brilliant, competitive, collaborative. Scientists who argue in conferences, who spend sleepless nights checking code and reanalyzing data, who doubt their own findings even as they defend them. They are not priests of absolute truth. They are builders of provisional understanding. And they know better than anyone that today's knowledge may be tomorrow's scaffolding. So as we absorb what Webb has revealed, galaxies too fast, stars too early, black holes too massive, we do not retreat into denial. We ask harder questions, we design better simulations, we build bigger telescopes, and we remind ourselves that the goal of cosmology is not comfort, it is clarity. The universe is not here to fit our expectations. We are here to match our theories to its reality. And that reality, as it unfolds before us, is more dynamic, more mysterious, and more astonishing than we ever dared to dream. If there is one truth the cosmos has always taught us, it is that humility is the key to wisdom. The light that James Webb collects has traveled across space for over 13 billion years, weaving through epochs and transformations before finally arriving at our detectors. It is a silent witness to the birth of galaxies, the ignition of stars, and the assembly of the vast cosmic architecture we now inhabit. To interpret that light, to read its ancient story, is a responsibility that demands not only technical precision, but philosophical reverence. What Webb has uncovered so far is just the beginning. Its mission is young, and with each new observation, it pulls more threads from the tightly woven fabric of established cosmology. Some threads snap under tension, others unravel entirely, revealing deeper structures hidden beneath. In the coming years, as more early galaxies are confirmed and as follow-up observations sharpen their redshifts and chemical signatures, we will either confirm the acceleration of early structure formation or uncover even stranger truths. New tools are coming. The ELT, the TMT, the Rubin Observatory, all will add new perspectives to the puzzle. Perhaps they will confirm that Webb's early findings were just extreme cases, outliers in an otherwise consistent universe. Or perhaps they will reveal that what we thought was rare is, in fact, common, that the cosmos regularly gives birth to complexity at speeds and scales we have never imagined. If so, our theories must evolve, and in that evolution there is precedent. The theory of relativity did not replace Newtonian mechanics, it expanded it. Quantum theory did not undo classical physics, it embedded it in a deeper framework. The Big Bang model, too, may soon find itself subsumed, not rejected, but refined into a richer, more nuanced story. A story that allows for sudden growth, unexpected emergence, and chaotic beauty in the very first moments of cosmic time. Perhaps in this new model, black holes will no longer be final states, but prime movers. Perhaps galaxies will be seen not as delicate accumulations, but as robust eruptions of energy and matter. Perhaps the early universe will be remembered not as a quiet unfolding, but as a symphony of extremes, a furnace of transformation where time and structure were born together in violent harmony. Whatever the outcome, we stand at a turning point, a moment when the questions outpace the answers. When data begins to whisper truths our equations cannot yet speak. And this moment, however uncertain, is a gift, because it reminds us that discovery is never finished, that the universe is not a solved puzzle, but a living riddle, one that grows more beautiful the deeper we dare to look. And so we arrive, not at an ending, but at a horizon, one defined not by the limits of space, but by the expanding edge of human understanding. The James Webb Space Telescope has opened a new chapter in our story, a chapter not just about what we know, but how we come to know. With every pixel of ancient light it captures, we are being called to a deeper humility, a sharper curiosity, and a more expansive imagination. We are learning that the universe is not merely vast, it is agile, unpredictable, and profoundly creative. The Big Bang Theory still holds. It remains the most powerful narrative we possess to explain the broad strokes of cosmic evolution. But just as the theory itself emerged from a challenge to the old paradigm of a static universe, so too may it now evolve in response to what we are witnessing. That evolution will not be easy. It will require open minds, courageous thinking, and the collaborative effort of astronomers, physicists, mathematicians, and engineers around the world. It will require letting go of cherished assumptions and being brave enough to entertain the impossible, because sometimes the universe chooses to be impossible. And yet, within this uncertainty lies a deeper truth. The cosmos does not owe us clarity. It offers only signals, rays of light, fields of gravity, ripples in space-time, and waits to see what we will make of them. The responsibility is ours. To build the instruments, to run the simulations, to ask the questions no one has asked before, to turn our eyes and minds toward the heavens, not with pride, but with awe. This is the great legacy of our species, not just that we exist, but that we wonder, that we look into the darkness and dare to seek the light, that we read photons like poetry and discover in their faint glow the fingerprints of creation. Perhaps someday we will look back at this moment as the beginning of a new cosmology, born not from certainty, but from courage. Until then, the stars wait. The galaxies sing their silent songs, and we, with our fragile minds and tenacious hearts, continue the oldest journey of all, the journey to understand where we came from, how it all began, and what, if anything, lies beyond. Let the search continue.